This is the Aftermarket Radio Network.
Welcome, everyone, to yet another episode of Diagnosing the Aftermarket A to Z. I'm Matt Fonsel, and it's a bold strategy, Cotton. Let's see how it pays off for him. That and more after a word from our sponsor, NAPA Autotech Training. Check out our NAPA Autotech Facebook page to find out the latest NAPA Autotech virtual class scheduled at a time that is convenient for you. Learn from the comfort of your home. All right, I am really going to try to tackle a topic I've kind of been avoiding. There's a fair number of messages and emails asking to talk a little bit about it. And I guess I'm not trying to be evasive here with the topic. It's fuel trims. And if we watch a lot of or read a lot of the professional forums, go to a lot of classes, we see and hear or read about people looking at fuel trims and making some pretty seemingly bold diagnostic decisions and showing a fair bit of accuracy. And I'll tell you, even at work, some of the guys want me to try to explain to them how I can hop in a vehicle, sometimes not make it out of the parking lot, and kind of know what's wrong. And I don't know that I can do that in an episode or a episode. I guess if I can lay some framework, I'll call that a win. The thing is, I guess like anything, the more you know, the more you learn, the more you see, the more nuance you become aware of, the less generalized you feel comfortable being. And that's some of my big struggle with talking about stuff like this, that eventually you have to factor in certain nuances. It's hard to just say this is this way and that is that way. And if you see this, then that. Certainly there are vehicles you can absolutely do that. Other ones is not. So you're going to be it's more data to factor into your next test, your next decision. So I'm going to give it a whirl. I think the first thing we have to talk about is what fuel trims are. And one of the very best descriptions that I've seen was by, I'm going to credit Matt Ragsdale on IATN. Maybe it came from someone else, but he's where I saw it. So that's who I'll reference. But fuel trims are an adjustment to the base fuel schedule. And if you start thinking about what affects the base fuel schedule, then we can't not discuss two primary different fuel systems, if you will, or fuel delivery or fuel control type of systems. One is speed density. These systems use a manifold absolute pressure sensor as a very high authority input, along with engine RPM. And the engine controllers usually are, I guess, I'm going to use this word, complex. I'm not talking so much about the guts of it, but the algorithms can be more complex, or usually are more complex. The other system is an airflow system or a mass airflow system. Its primary inputs is the mass airflow sensor and the crank sensor, RPM. Is there more details to that? Sure. But I think just for a point of conversation, those are the two heavy hitters. Nowadays, isn't even nowadays. Nowadays, I mean, even 20 years ago, I guess, you started to see airflow systems with speed density modifications, or vice versa. You saw, or vice versa. And different weight given to one strategy than another in different ranges or situations, be it load, temperature, stuff like that. I don't mean that to be overcomplicating matters. It's just be aware of it, that you may have a mass airflow sensor and a manifold absolute pressure sensor. It might primarily be an airflow system with speed density modification, or it could be fundamentally a speed density system with mass airflow modification. And a lot of this was born of cam phasing or valve timing, just to help better determine load ranges, to better calculate fuel delivery more accurately, namely for that base fuel schedule. We're going to look to the exhaust, specifically the oxygen sensors or lambda sensors pre and post CAT to start modifying that. And that's where we get into fuel trims, right? Short term and long term. Short term, I think you might read into that as very literal. But a lot of times, if not most times, short term drives the oxygen sensors or the air fuel ratio sensors, if that makes sense. That's usually done purposefully to achieve some sort of response. The other one, maybe you could take a little more literally, is more of a permanent type of adjustment. Okay. So the PCM and ECM engine control module finds that it needs to add 10% to get this into what it feels is lambda. By what it's measuring, it needs to add 10%. After a while, long term is going to help try to drive short term back down close to zero. So you'll see a long term adjustment for, we'll just say 10%, just to kind of keep this, I think, in more simple terms, right? I think the one thing that just gets rough in talking about this is there is complexities. There's things going on they don't tell us. I'm not trying to just blow this stuff way out of proportion, but you'd have to keep this in the back of your head that there is things going on behind the scenes, if you will. Do we necessarily need to know? Probably not for the vast majority of what we do. It's just when you start getting out into certain extremes or non-normal operating where you see certain responses or behaviors, then knowing more helps explain the whys and the why fors. I don't know that we need to get into that, quite honestly, at least not now. Long term is kind of working to keep short term fairly close to zero, okay? Whether it's adding or subtracting based on how short term's driving. You can see this on some scan tools with really good refresh rates or the ability to minimize the number of PIDs to increase the update rate. You can a lot of times see short term how it kind of drives the oxygen sensors, and honestly a little bit with the air fuel ratios sensors, because there is perturbations going on, and some of them are natural, but some of them are driven. All right, so I think we'll just start with how about speed density, where we have a MAP sensor. It's measuring the pressure in the intake. If something affects the amount of air going into the intake, whether that's through the throttle plate or not, it changes the pressure of the intake manifold. More air would get more fuel. So if we have a vacuum leak on a more purely speed density system, you're probably not going to see that in fuel trims because more air is getting in, therefore more fuel. You would see elevated engine RPM. And a classic scenario, especially older vehicles, was you would see maybe higher RPMs at idle with whatever's controlling the idle, an idle air control motor or solenoid, run all the way in or at its lowest setting or very, very low, trying to compensate. It's trying to cancel out the amount of air bypassing the throttle plate. It's trying to make that vacuum leak a less of a contributor, if you will. And the reason I phrase it that way is when I talk a little more about airflow systems. So now we have that type of a scenario. There's other situations where pressure can go up and cause more fuel, but we're not actually mixing it with oxygen, if that makes sense. So just think about an EGR hanging up. You're now increasing the pressure in the intake. It's going to deliver more fuel. It's not going to cause RPM to go up. It's going to cause a kind of a rich condition. Okay? More fuel than air. So we might see, if this is happening at idle, we might see the whatever in control of the idle backing out, trying to get more air in, mostly for RPM. And then also we're going to see our fuel trim start changing. It's going to start pulling fuel back. That's a clue. Other issues, vacuum leaks that affect either cylinder specific or, more importantly, hit the map sensor hard. A lot of map sensors, especially back in the day, but even some newer ones, they get a leak that only affects the map sensor itself or affects it heavily. Maybe not all by itself, but if it affects it heavily, it's going to see more pressure, even though that pressure is not actually in the intake. So what's it do? Adds fuel, and now we see fuel trims pulling fuel away. We really don't see a whole lot of speed density anymore. Primarily what Chrysler, I think even Honda has kind of gone away from it. Situations where it's going to be adding fuel is, do we have a skewed map sensor? One good way maybe to start testing that is to look at it key on engine off. Does it match baro? Or if it is the baro input, is its output reasonable for whatever altitude you're at? And can you take it in either with a vacuum gauge or even just on a test drive? Watch how it responds. And just a little off track, not fuel trim related, is if you were to have a restricted exhaust on a map sensor vehicle, if you were to watch the map sensor versus the throttle, for the most part, they kind of match each other, right? Normally. If you have a restricted exhaust, an old test back in the day was to put a vacuum gauge on the intake and rev the engine up. And if the vacuum gauge needle started trending down so that the vacuum's lower or the pressure is higher, that was an indicator of restricted exhaust. Well, we can do that with a graphing scan tool. We can graph them against each other. And as you're gradually getting in to the throttle and loading more and more and more, you would expect the map to kind of follow the throttle. Until you're really in it, really loaded down, you're not going to see very close to atmospheric in the intake. But if you restrict the exhaust, now you're really just partially into it and starting to see atmospheric pressure in the intake. And then that ends up being a pretty nice test. In very rare cases, I think I've seen it once. It was a cam phasing issue, but there's other clues, including codes with cam timing. So it's a pretty good test for restricted exhaust on a speed density system. I'm not just trying to rattle off like bullet things. I'm just trying to get you to think a little bit about what it's looking at and what the fuel trims will do. NAPA Autotech training sessions are being conducted day and night in a town near you. This training caters to every level within your organization, be it a mechanical assistant, a mechanical specialist, a technology specialist, or a driver safety calibration specialist. Imagine a one-stop shop training partner in NAPA Autotech that will lead your team to a path to greatness. Autotech's entry-level Build-A-Tech classes convert the untapped potential of your new hires into money-making mechanical specialists. Autotech's higher-level tech update classes introduce specialists to the world of ever-changing technologies, which prevents your shop from getting technologically stagnant. Remember, if you're not moving forward, you're falling behind. And, turning to the front of the store, the Autotech Service Advisor class is an awesome way to hone your client advocate skill set, ultimately benefiting the customer through an improved vehicle repair experience. But it doesn't stop there. Imagine an electric vehicle class that takes your specialist well past the mundane, yet necessary safety topics. Well, it's here. Autotech's EV Ready Training is a week-long curriculum that takes participants through a hands-on experience involving hybrids and electric vehicles. The session kicks off with the use of PPE and proper tooling while touching on required OSHA regulations. Then, the students dive into the lab vehicles to gain knowledge of the common high-voltage components on EV and hybrid vehicles and their function. Attendees will be taken on a path exposing them to different electric vehicle manufacturers to compare component form and location. Additionally, information about Level 1 and Level 2 charging systems will be included, along with a quick look at DC to DC charging. The operation and maintenance of subsystems are explored, including the different modes of Tesla operations, and so much more. So what are you waiting for? Commit to taking your business to the next level with NAPA Autotech training. Ethanol. I don't know how many people run into this, and this can be fairly true of both systems, speed density and airflow. But if you have somebody that's been trying to save money by putting oxygenated fuel into their gas tank, you'll see the fuel trims go positive. They're adding, pulse width, if you will. They're adding fuel, but generally it's the same. It doesn't change, meaning the amount it's adding at idle is not a whole lot different than what it's adding under part load, under cruise conditions, right? It's pretty much the same all the time. Fuel delivery issues, like a restricted fuel filter or a fuel pump that can't deliver. That might be a scenario where at idle, everything looks good, but you start getting into it more and more and more. And by getting into it, I don't even mean like revving it up the red line or anything. It's just loading it down. If there's a good hill to pull under varying speeds, so like kind of where I live, I've got one really nice steep hill that the speed limit's, 30. I have another pretty darn good hill that I can go highway speeds. So, I have options. And then, of course, I have a few nice straightaways. If you can mimic that, those are good test drive scenarios. And what you'll see with like a fuel pump that's kind of worn or binding is that at idle, it can provide plenty of fuel. Light load, putzing around town, fuel trims look great. Take it out on the road, start getting into it, and start really loading the vehicle down, loading the engine down. You start to see it adding more and more, fuel trim. See everything trending up as we move through I'll probably get some static for this, but in the interest of conversation, moving through the map, as it's moving through fuel delivery map, different cells, you're going to see jumps, you're going to see changes. Many of these already learned unless you've, reset the memory, and then you're going to see things adjust, but still, you're going to see it add more and more fuel to try to make up for what the fuel pump's lacking. You'll also see that on airflow. So they mimic each other. And then I think we have to jump into the airflow system. Mass airflow sensors take a sample of the air going in, right? It gives an indication of how much air the engine is ingesting. I think right away, and I kind of started with this in speed density, is the obvious difference for vacuum leaks. Speed density, it's not really going to affect the fuel trims for the most part, depending on where the vacuum leak is. But in general, it doesn't affect airflow systems. This is something that's called pirate air, or at least unmeasured, right? We're bypassing where the air is going through, where we want most of the air to go through. Okay, depending on certain vehicles, we may have situations where there's a calibrated vacuum leak that isn't measured or sampled. But for the most part, we want all that air going through the mass airflow sensor, where it can at least take a sample. If we don't, now we have air going in that's not measured, pirate air, that it can't see it. Of course, it's not going to add the appropriate amount of fuel. So therefore, we have a lean condition. And that's one of the big differences. We have a lean condition at idle where the vacuum leak, the size of it, as a relative or as a ratio to the air going through the mass airflow changes the more we open up the throttle plate, if that makes sense, right? The throttle plate is relatively closed at idle. Maybe there's an air control motor or something involved, a solenoid, maybe not. That vacuum leak is going to make up a larger percentage of the air going into the engine with the throttle plate closed or close to closed at idle position. Then if we crack that throttle open under load, especially, even 25, 30%, just a little bit. Now that air leak has less effect. And now what you would see is at idle, fuel trims are fairly positive, but under light load, they go almost perfect. Maybe slightly lean, maybe not. Depends on how big, right? That's a pretty good indicator. If you're bringing a vehicle in, setting lean codes, start it up, you're looking at your fuel trims at idle, they're all adding however much, a lot, quote unquote, a lot. And not saying this is the end all be all, but you could put that thing in reverse, power brake it a little bit, half throttle or so, and just see what the fuel trims do. Otherwise, just take it for a quick drive around the block. What happens? and those fuel trims go almost perfect under light throttle, part throttle, it's a good indicator to come back and start looking for a vacuum leak. Pop the hood, see if you can hear one, get the smoke machine out. It's a fairly good indicator. Another one that drives coworkers bonkers is certain car lines have a phenomenon, if you will, where it may set rich codes and lean codes. And if you look at the fuel trims at idle, it looks like it's pulling back quite a bit of fuel. But you go on a test drive, and the more load you put it under, the more air they're trying to pump into the engine or pump through the engine, the more positive they go. This is kind of a phenomenon that you see with contaminated mass airflow sensors. And there's a host of reasons given to us why this happens. I don't know how important it is for us to really know. The leading cause I know of is the leading theory is mass airflow sensors don't measure air just one direction. All right. And at lower RPM, specifically idle, you have something called reversion, where air's pulsing in, kind of goes in and out, back and forth, back and forth. We'll just say the way they compensate for that, when the mass airflow sensor gets contaminated, throws that calculation, or really throws that strategy off. And we get it to where it's now overcompensating or over-calculating, over-measuring the amount of air going into the engine. So it starts pulling it back. And then, of course, you take it out and you get less reversion, more air coming in one direction. It can't measure it accurately. Therefore, it undercalculates and needs to add more and more and more, if that makes sense. This is very prevalent on GM Ford. I've seen it on other car lines, and it's just something to be aware of. It's something to keep dibs of, something to look for. If it's got lean codes, when does it set it? It's got rich codes, when does it set it? It's got both. You see this. Pop that mass airflow sensor, look, is it dirty? I would recommend replacing it if it is. Some people clean them. It's one of those things where you got your camps. People clean them, never had a problem. People that have cleaned them, and especially in emissions areas, run into problems because skewing, if you will. So, I think the right thing to do would be to replace and then also find out why it got contaminated. Sometimes it's just time. Other times it's a K&N filter, poorly maintained K&N filter, or improperly seated air filter, or the missing screws in the air filter housing, stuff like that. There's contributors. Another phenomenon is on V-style engines. And I might be jumping around a little bit, but I guess I bring these up because I feel like if you can kind of grasp what's going on, what the strategy is, how the engine control module thinks, that it makes it more and more understandable. It makes these more usable. And when you start thinking that way, you can kind of step back, and what you're seeing in the bay tomorrow or the next day, you can take some of these not as bullets, but just as frameworks to what might be going on. And maybe you can start thinking a little bit more like the system and make a really either an accurate call, or what the next test should be. I know what the next test should be. So I think we'll start out with one scenario and then we'll go to another scenario. The first one is, and these are on V-style engines. This is very important. These are V-style engines that have one mass airflow sensor. If you have a cam timing issue where one bank is affected and not so much the other, at idle or low loads, you're going to see a phenomenon where you get what we call fuel trim split, bank to bank split. What I mean by that is not that they're so much different, but what you will see is one will be fairly positive and the other one will be fairly negative. With cam timing, you see this at low loads, idle, light loads, but the more load, the more air you run through it, the better the trims get. So I want you to think about this a second. Think about this on an airflow system. What does it want? Okay. And we do have all the air going past the mass airflow. Now, don't kid yourself. The mass airflow sensor is not measuring all the air, but it has that sample. There's an assumption that has to be made by the engine control module, right? It has to assume that all the air is going past the mass airflow sensor and it is being equally divided bank to bank. Now, we can get into situations, or not even situations. We can get into the fact that the air delivery to each cylinder isn't exactly the same. Okay? It just isn't. But again, for the sake of conversation, the engine control module is going to assume that the airflow, the amount of air ingested, is going to be equally divided, be it to each cylinder or maybe better yet, bank to bank. If we take the cam timing and we affect that airflow for one bank, we have X amount of air going through the airflow sensor. PCM, ECM, engine control module makes that assumption that the same amount of air is going to one side as the other, but in reality, it isn't. One side is ingesting less air than the other. That starts throwing the trims off. Does that make sense? Let's just toss out some math, which I'll probably pick horrible numbers, but let's just say that this vehicle at idle is pumping through 6 grams per second. The cam timing is off on one of the banks. Let's just say now, instead of ingesting 3, 6 divided by 2 would be 3 grams per second on each side. The one bank only ingests 2. The other bank is ingesting the 4. I'm not implying that because the one side is lower that the other one just has to eat this 4. That's not what I'm saying. Let's just say on the normal operating engine, maybe it ingests 7 or 8. The point being is they're not the same anymore. The PCM, the engine control module, is assuming that it's equal. That would be 3 and 3. It's not. It's 2 and 4. One side is getting fuel for 3 grams per second, but it's only ingesting 2. The other side is also getting fuel for 3 on the base fuel schedule, but it's actually using 4. See what's going on? See what the fuel trims are doing? One side is going rich. It's going to start pulling fuel back because it's only using 2. The other side has add. It's adding more fuel because it's lean. It's just a really good indicator. It's a good indicator to run the car back in and do a relative compression test and look to the compression peaks. Or if it's one of certain engines, I guess you can yank the timing covers off or chain belt covers and verify visually. But yeah, you can have situations where the cams themselves are off, but the relectors aren't. You know what I mean? So it's a good test to have in your pocket. Let's take a similar situation though and say we don't see this split at idle. At idle, the trims look perfect. This is still a V style engine. It's got to be a V, or at least have 2 banks. You know what I'm talking about. Idle's fine, but we start pushing air through this thing. We start loading this thing down. We start seeing the fuel trim split. It's just like the one I talked about, only not at idle. It's under load. The more load it seems, the worse it gets. Maybe we even start racking up misfires on one bank. And think about that. Idle's good now. But when we're trying to push air through there, now it kind of goes sideways. Now one side's going rich and one side's going lean. We're seeing a lot of negative trim on one bank and a fair bit of positive on the other. What could cause that? The ones that know, I can hear you screaming it. The ones that don't, think about that a little bit. What would be fairly dependent? What would allow flow at low volumes, but start restricting the more and more we try to push through it? And would only affect one bank at a time, or just one bank. If you're thinking exhaust, specifically catalytic converter, you'd be right. Think about that. At idle, it's not that much airflow to get through that catalytic converter. But we start really stressing it out. We start pushing more and more. All of a sudden, we start seeing this fuel trim split for the same exact reason. The numbers are much higher, but it's based on the assumption that the engine control module really has to make that all the air is going past the mass airflow sensor and being evenly distributed for the most part, bank to bank. It's a very powerful tool. And I guess the only other thing I think I'll run past you, because I don't want to go terribly long with this because this could be dumping a lot of stuff on you to process. And I think this goes for speed density and mass airflow. Certain vehicles are prone to having a failed fuel injector. And they fail in such a way where they go low impedance and end up delivering more fuel. What happens to the fuel trims? And the classic example that I see, or scenario I see, is it comes in with a code for misfires on a cylinder. We'll just say it's a 4-cylinder engine, and for whatever reason, it's misfiring on the cylinder. Well, really, it's kind of racking up misfires, we'll say, on 1, 2, 3. I'm just kind of pulling this out of my tail because there's more than one car line that does this, but we're seeing misfires on 1, 2, 3. And you look at the fuel trims and they look okay. They're not terrible. But it's missing on 1, 2, and 3. Not like dead misfire. 4 doesn't miss a beat. And ends up, the problem is you end up scoping the fuel injector current or voltage if you're looking at the inductive kick. And you find out number 4 went low impedance. This could be on a bank style engine too. A V8, 1, 2, 3, 4. I don't even say that to kind of give away the car line, because actually that car line, I have seen that on a bank. So whatever. You see the misfires on 1, 2, 3. 4 doesn't miss a beat. And you scoped 4 because you end up focusing on 1, 2, and 3. But if you were to scope cylinder 4, you would see a low inductive kick. You would see high current. You would definitely see a sharp rise at the beginning of the current ramp. And it ends up, number 4 goes low impedance, so therefore it delivers more fuel. So the fuel trims start pulling back, leaning it out, and causing the other 3 to go lean and start misfiring, even though fuel trims look great. So, these are just a couple of the things that I look at when I go on test drives. Do I do the flat rater test drive? In certain situations, yes. A lot of times it's just going for a 5-10 minute test drive through varying conditions and just graphing the fuel trims. And depending on the system, maybe I compare it to throttle, maybe I compare it to RPM. But a lot of times it's just looking at the fuel trims, short term, long term, through varying conditions. And I just kind of watch what they do when they do it. And it can give you some very, very good angles. I think I'll leave it at that. If this is up your alley, like where this is going, and would like more on that, please let me know. Send me messages via Facebook. Send me an email, mattfonslowpodcast@gmail.com. Yeah, just let me know if this is kind of up your alley, and see if we can go a little deeper into fuel trims. The further we go, the more nuanced it gets, or more vehicle specific it can sometimes end up being. That'll get a little rough, but not impossible. But I think for the most part, hopefully this sets you on a good path, especially considering what they are in response to base fuel schedule. I kid you not, I read that on IATN many years ago, and it hit me like a ton of bricks, and it really helped things make more and more sense. So thank you to Matt Ragsdale for doing that. And I will leave it like that. Thank you very much for listening. If we could take a moment to thank our sponsor, NAPA Autotech Training. And also thank you to the Aftermarket Radio Network. And until next time, take care.
You've been listening to Matt Fonslow, diagnosing the aftermarket A to Z on the Aftermarket Radio Network. Follow Matt on your favorite listening app. He's very interested in what you have to say. Let him know what you'd like him to cover and come on the show. Matt is all for advancing the aftermarket. Find Matt Fonslow on social media and connect, or on aftermarketradionetwork.com.